Welcome to this video presentation on Introduction to Organic Chemistry. In this video we'll be looking at the hydrocarbons, which are the first and simplest of organic molecules. Our learning intentions for this video are to describe the bonding of carbon in organic molecules, draw and name the first 6 alkanes, draw and name simple branched alkanes, and define the term isomer. We'll start by looking at the electron arrangement of carbon, which has 2 electrons in the first energy level and 4 electrons in the valence shell. This means that carbon requires 4 more electrons to complete its full valence shell, and because of this, carbon will form 4 covalent bonds to other nonmetal atoms like hydrogen, carbon, nitrogen, and oxygen. We can see that in these simple examples of organic molecules. This first molecule is methane. As you can see, it has 4 covalent bonds to 4 hydrogen atoms. This molecule is formaldehyde. Again, 4 covalent bonds around the carbon, including 1 double bond to an oxygen atom. This molecule is ethene. Each carbon in this molecule has 4 covalent bonds around it, including the double bond to the carbon atom. This molecule is aminomethane. Again, 4 bonds around the carbon, including 1 single bond to a nitrogen atom. You'll start to recognize a pattern, in that carbon always forms 4 bonds. Also, hydrogen always forms 1 bond, oxygen 2, and nitrogen forms 3. If you remember these simple bonding rules, then it will make it easier for you to draw correct organic molecules throughout this unit. So remember those basic rules: carbon 4, nitrogen 3, oxygen 2, and hydrogen 1. Now we'll look at some representations of the simplest organic molecule, which is methane. CH4, 1 carbon and 4 hydrogens. Here are some different representations of methane. This first representation is the simplest one and the one we're most likely to draw, showing the 4 covalent bonds around the carbon. But this representation shows an incorrect bond angle of 90 degrees. This representation is better. It shows the tetrahedral carbon with a bond angle of 109, but it's a bit harder to draw. This is a ball and stick model. Again, it shows the way that the carbon and hydrogen atoms are bonded together and shows the tetrahedral carbon. This space-filling model is a little more confusing, but it does show the overlap between the carbon and hydrogen bonding clouds. So there are 4 single bonds around the carbon atom. This forms a tetrahedral carbon with a bond angle of 109. Now we'll look at the first of the series of hydrocarbons called alkanes. Hydrocarbons are molecules that are made of carbon and hydrogen atoms. Alkanes are hydrocarbon molecules that have single bonds between each of the carbon atoms, shown by a single line. This is methane, the first of the series of alkanes. As you can see, there is 1 carbon atom and 4 covalent bonds to hydrogen around it. The formula for methane is CH4, 1 carbon with 4 hydrogens. The next molecule in the series is ethane. Ethane has 2 carbons bonded together with a single bond, and 6 hydrogens filling up the rest of the bonding spaces. So ethane has a formula C2H6. If we add a 3rd carbon to the chain, we'll get the 3rd molecule in the series, which is propane. 3 carbons bonded together in a line with single bonds, and 8 hydrogens filling up the bonding spaces. This is propane. Adding another carbon to the series gives us our 4th molecule, butane. 4 carbons bonded in a line with 10 hydrogens filling up the bonding spaces. So butane has C4H10. You'll notice that the chain increases by 1 CH2 group each time. So the next molecule in the series will have 5 carbons and 12 hydrogens, and will be called pentane. Let's look at some 3D models of these molecules. In this first model, we're looking at ethane. I've chosen this animation because it shows the rotation of one of the end groups. This is an important idea, that the carbon-carbon single bonds allow for free rotation around the atoms. So that even though we draw models and molecules in static, stationary positions, in reality all the bonds are rotating and moving. It's sort of a useful idea to be aware of later on. If we look at the next molecule, which was propane, we'll see this start to form, with the tetrahedral carbon starting to form the beginning of a zigzag. That will be more clear when we look at butane. 4 carbons bonded in a line, each carbon being tetrahedral at 109 degrees, gives us the zigzag shape. And if you keep going down the series, the zigzag just gets longer. So it's useful to know that even though we draw them in 2 dimensions with 90-degree bond angles, in reality they look a little bit different and are definitely 3-dimensional shapes. Now we'll just consider one more type of alkane, and that is cyclic alkanes. Alkanes can be cyclic, they can actually form rings. This molecule is cyclohexane with 6 carbons bonded in a ring structure. This structure has a close to 109-degree bond angle, so it is quite stable and common in many organic molecules. But there are other ring structures too. You can have ring structures with 5, 4, sometimes even 3 carbons, but those structures are not very stable, as now the bond angle is significantly smaller than the 109. Now we're going to move on to how we name straight-chain alkanes. You'll see a table like this in your notes and in many other revision study guides for organic chemistry. The names of alkanes are based on the number of carbon atoms that are in the chain. 1 carbon meth, 2 carbons eth, 3 prop, 4 bute, and so on. It is not easy to remember the first 4 because there is no logic or order to them, so sometimes a mnemonic can help. I like monkeys eat poisonous bananas. It sort of helps meth, eth, prop, bute. After that, you can apply the maths rules, pentagon 5, hexagon 6, heptagon 7. You're expected to at least know up to 6, but most can actually know more than that. Alkanes follow a general formula, CnH2n plus 2. So for every carbon in the molecule, there is double plus 2 hydrogens. We identify the parent chain, which is the longest number of carbon atoms in the molecule. This is identified and named using the appropriate prefix to indicate the number of carbon atoms it is. So for pentane, there would be 5 carbon atoms in the molecule, and with double plus 2 there must be 12 hydrogens. Heptane with 7 carbons would have 16 hydrogens. Can you name these 2 molecules? If you've done it correctly, this first molecule has 2 carbons in it, so this was based on eth. It's an alkane with carbon-carbon single bonds, so this molecule is ethane. The other one with 4 carbons is butane. You should now pause and take a moment to draw out the first 10 of the alkanes in the series, naming each one and writing the formula of each one using the general formula. Now we're going to look at branched alkanes, which introduces a new concept called an isomer. Isomers are molecules which have the same number of atoms in them but with a different arrangement. We're going to use butane as an example to show you this. This is a molecule of butane with 4 carbons and 10 hydrogens. This is a straight chain hydrocarbon because all the carbons are joined in a line. The parent chain, being 4 carbons long, is therefore butane. But there is another way that we can draw 4 carbons and 10 hydrogens. And this is it. We can put 3 carbons in a line and 1 carbon hanging off the middle one. This carbon forms a branch. So this is a branch chain alkane. The parent chain in this molecule is 3 carbons long, so it's called propane. The branch is 1 carbon, so it's a methyl group, CH3. This molecule would be called methylpropane. If we were to look at it in 3D, we would see something like this, again with each carbon being tetrahedral. So there are 2 ways of drawing C4H10, and these 2 molecules are isomers of each other. They have different names and they have different properties. Let's look at another example, which is pentane, C5H12. There are 3 ways that we can draw 5 carbons and 12 hydrogens, and these are the 3 isomers. This molecule is a straight chain molecule, so it has the 5 carbons joined in a line. This molecule, we have 3 carbons in a line and 2 methyl branches hanging off the middle carbon. This molecule has 4 in a line with 1 methyl group hanging off the second carbon. So these 3 molecules are all different, so they are all isomers. They all have different names and they have different properties. But not every example that you can draw would be an isomer. You need to be careful. Here is an example of another structure of C5H12, but this is not an isomer. This molecule is actually pentane drawn in a slightly different way. There are 5 carbons in a line. All that's happened is that one of the bonds is rotated, put the CH3 group down the side. This is just another way of drawing pentane. These two molecules are exactly the same as this one. 4 carbons in a line with a methyl group on the second carbon. They are the same molecule but just drawn from slightly different angles. So it's important to check. Each isomer should have a totally different name. If the name is the same, then it's not a new isomer. It takes a bit of practice. Be patient. The last thing we'll look at is how we name these branch chain alkanes. Here are a series of 3 rules that we use. You should take a moment here to pause, write these 3 rules out, or take a screenshot, and we'll be using those rules in the next slide. The first thing is to identify the parent chain, which is the longest sequence of carbon atoms we can identify, and we name these using our correct prefixes. The second step is to identify the branches. Name these branches using a correct prefix, but change the ending to -il, so for 1 carbon it would be methyl, a 2-carbon branch, ethyl. The third step is to number the parent chain to give the branch the lowest number possible. Give each branch its own number, and if there are identical branches, we'll use a prefix, di or tri to show this. Let's look at some examples. This first molecule has 3 carbons bonded in a line. That's the parent chain, so this molecule is based on propane. There is a CH3 group, which is a methyl branch on the second carbon in, so this molecule would be called 2-methylpropane. The next example has 5 carbons in a line, so the parent chain for this one is pentane. Again, there is a methyl group, but it's on the 3rd carbon along, so we call this molecule 3-methylpentane. The next molecule has 4 carbons bonded in a line, so its parent chain is butane. There is a methyl group here on the 2nd carbon in, so this molecule is called 2-methylbutane. Be careful. If you number the molecule from the other direction, you get 3-methylbutane, which is not the lowest possible numbering sequence, so check both sides so you get the lowest number. The next molecule has 4 carbons in a line, so its parent chain is butane. There are 2 methyl groups on this molecule, here and here, so we need a prefix di to show the 2 methyl groups. 1 methyl group's on carbon 2 and 1 is on carbon 3. So this molecule is 2,3-dimethylbutane. The next molecule has a parent chain of propane. There are again 2 methyl groups, so we need dimethyl, but now both methyl groups are on the 2nd carbon, so this molecule has 2,2-dimethylpropane. Note, 2 groups, 2 numbers. Each group must have its own number. The last molecule is this one here. It has a parent chain of 5 carbons in a line. Now there is an ethyl group on the 3rd carbon, so we'll number this molecule as 3-ethylpentane. In summary, what we've learnt in this video: carbon always forms 4 covalent bonds. Hydrocarbons are molecules made of carbon and hydrogen atoms. Alkanes are molecules with single bonds between carbon atoms. Straight chain molecules have their carbons bonded sequentially in a line. Molecules with side groups are called branched. Isomers are molecules with the same number of atoms but with different arrangements. And branches are named using a prefix and numbered according to which carbon atom they are bonded to in the parent chain.